Hi everyone, this is team of Ju and So, Jian Kim and Hyun Lee, and we're going to present the QP-based MPC formulation for control fine nonlinear system. So the whole of the motivation is that we're trying to come up with the MPC for the nonlinear system, and due to the convexity of the optimization problem of the nonlinear system, it is really high likely that it actually converges to the local minimum or even do not reaches the global optimum within the given sampling time. And it is also really challenging that to calculate the invariant set for MPC, so we could not guarantee the feasibility, and also stability is still debatable. So within this sense, we actually propose the QP-based MPC for controlled fine nonlinear systems. And our key key idea is that we're trying to combine the phonemic linearization and the linear MPC in here. So the whole point is that the phonemic linearization is actually enables the system to be linearized. And if you have the linear MPC, then we could come up with some theoretical analysis of how the feasibility looks like or stability of utilizing its convex property. So let's go over some backgrounds over here. We define the control fine nonlinear system, which is given as x dot equals to fx plus 2x view, and we have observations, which is y equals to yx. And we could actually formulate these problems into to y dot equals to nx plus mx multiply u, and to linearize the systems, we use the phonemic linearization, which is y is given x in these forms. So finally, we have some desired linearized dynamics, which is equals to y2 dot equals to minus k1 y minus k2 y dot plus u prime, which is given as equation 3, and this actually enables to come with the typical and conventional formulation of how the linearized dynamics looks like in equation 4. So to come with the MPC formulation, we describe everything. We describe the dynamics given as equation 5, and we describe the control input given as equation 6. And finally, we have the MPC formulations at the equation which is stated in the last slide. And we designed the control input and terminal set as given in the slide. So first, for the control input set, we construct the equivalent set of the UT with respect to the UT prime. As xk is accessible to the kth number MPC, we could construct two equivalent set over in here. And for the terminal set design, we just uses the maximum invariant set for the closed loop systems under the unconstrained LQR control law. To check its theoretical analysis is valid or not, we have come with some really simple numerical experiments. So for given to example, which is simple nonlinear dynamics, which we have observations y equals to x1 in here, we have two experiments with the strict input constraints and strict state constraints over in here. So the first one with the strict input constraints, we also check that the trajectory actually converges to the origin, which is given as the figure 1 and 2, and also the input goes to the 0 as time goes by. And the sampling time is equals to 10. And for the second case, which is we have strict states constraints, it is also is to check that our constraints also converges to the origin as time goes by, and the input also in figure 4 and 5, and also input constraints. The inputs also converges to the 0 as time goes by. For the visual directions and conclusions, so finally we have come with the QP-based MPC controller on the feedback linear systems, and we also have done some numerical experiments to check its stability and feasibility of different input and state constraints. And there is some possible feature work in here. We could come with some adaptive control with system identifications, and or either robustness analysis to system disturbance and sensitivity analysis using different approximation methods. Thank you so much.